Okay, let's go over the answers from the previous week's questions. Um, so, first one's just on Newton's first law. If you remember, I know it's been a while since it's been off for the Easter break. Newton's first law just states what happens objects when the resultant force, the overall force, is zero. And what it says is they can do two things. They can either be stationary if they were stationary, or if they were moving, they continue to move. They don't stop, but they continue to move at the same speed, so they don't get faster or slower in the same direction. So first one just has to explain how it applies to car that's stationary at traffic lights. Well, it's stationary, therefore the resultant force is zero, but that's because there's no forces pulling it forwards and there's no forces pulling it backwards. Okay. However, car traveling at a constant speed of 30 miles per hour, the resultant force is also zero. However, what you should say in your answer is that there's a forwards force due to the engine of the car turning the wheels, but there's also a backwards force due to friction. And those two forces will be the same size, so they'll cancel each other out. So the overall resultant force is zero. So you really should be talking about the resultant force in both cases being zero. Describe in terms of the size and direction of the forces that act on you when you're standing still. If you're still, once again, key thing about Newton's first law, resultant force is zero. How is that possible? Well, it's not because there's no forces acting on you, because you have your weight acting downwards. However, if you're standing on ground, the ground pushes back up. It's called a reaction force. Exactly the same size as your weight, so those two forces cancel each other out, meaning that the resultant force is zero. An astronaut in deep space has no forces at all acting on them, therefore the resultant force will be zero. Therefore, Newton's first law applies. Describe her possible motion. Newton's first law says that she can either be stationary, if she was stationary, or she can travel at a constant speed in a straight line. Okay. Question 4, one that people often get wrong. Skydiver jumps out of an aircraft and is pulled down by her weight. So as soon as you step off that aircraft, there's a force downwards that starts accelerating you downwards, and she gets faster and faster and faster and faster and faster. But the faster you get, air resistance gets bigger. Okay, so if you're traveling quite slow, it'll be small. The weight will be bigger, therefore you'll still be getting pulled down. You'll get faster and faster and faster. The faster you get, bigger air resistance get, and eventually you get to the stage where those two things are the same size, they're acting in opposite directions. So key thing about Newton's first law is the resultant force is zero. And Newton's first law says you can do two things. You can either be stationary or you can travel at a constant speed in a straight line. No one in their right mind would jump out of the aircraft thinking they're going to be stationary somewhere before they hit the ground. Therefore, in this case, what happens is when you jump out of an aircraft, you get faster and faster and faster, but just up to a point. And then once this happens, that the resultant force is zero due to air resistance, then for the rest of your journey, you won't get any faster. You'll travel at constant speed, and that's sometimes referred to as terminal velocity. Diagram below shows a car traveling at a constant speed of 70 miles per hour. What is the thrust, the forwards force, in the diagram that must be produced if the drag is 2,500 newtons over here? This looks like it's important, but it's not. It doesn't matter what speed it is. The key thing in that sentence is actually the fact it's at a constant speed. It's not getting faster, it's not getting slower. Therefore, Newton's first law tells us the resultant force is zero. For the resultant force to be zero in this case, T here must equal 2,500 newtons, so that this force and this force cancel each other out. Okay, next one looks at what happens when there's an unbalanced force. And we say that unbalanced forces, Newton's first law doesn't apply. So it doesn't stay stationary, it doesn't stay at a constant speed. What happens is the speed changes, and we refer to that change of speed as an acceleration. And when the acceleration is 4 meters per second squared, what we mean by that is that the speed will get bigger, so will increase by 4 meters per second every second. So speed at the start would be 0 meters per second. 1 second later, it'd be 4 meters per second. Another second after that, it would be 8 meters per second. Okay, so the speed increases every single second by 4. Train decelerates, that means it gets slower at 2.5 meters per second squared. What does this mean? Well, it's kind of the opposite as above. So the speed decreases by 2.5 meters per second every second. Okay, so in this case, if it was traveling at 10 meters per second, after 1 second it would decrease by 2.5 to 7.5 meters per second. After another second it'd be down to 5 meters per second. After another second it'd be down to 2.5 meters per second. Another second after that it would stop. If an object accelerates, what direction is the resultant force? Objects accelerate in the direction of the resultant force, so the resultant force must be forwards. For it to slow down, then the resultant force must be backwards. Car accelerates from rest at an acceleration of 5 meters per second squared. What will be its speed after 4 seconds? Well, it starts at rest, so initially its speed 0. After 1 second, it will increase by 5, because that's what that acceleration means. After another second, it will increase by 5 to 10 meters per second. After another second, it'll be up to 15. And after another second, it'll be up to 20. So it increases by 5 meters per second every second, which means after 4 seconds, it's going to be up to 20 meters per second. Car is traveling at 20 meters per second and decelerates at 2 meters per second squared, which means its speed decreases by 2 each second. What will be its speed after 4 seconds? Well, let's do this. 20. After 1 second, decreases by 2, 18. After another second, 16. After another second, 14. And after another second, 12. Okay, so each of the steps is 1 second. So after 4 seconds, its speed will be 12 meters per second. How long will it take it to stop? We could do our little timeline and kind of keep going like this. But you know, starts at 20, gets less by 2 each second. That will mean it will take 10 seconds for it to come to a stop. Okay, you should mark your own work. We're going to then move on to Newton's second law, which kind of follows on from this lesson. So if you're kind of a little bit ropey on some of those answers, go back and rewatch the videos from the previous week before Easter before you look at this week's videos.